Hi, I'm Lior from Imuni, and I'm going to talk about how to test microservices. Now at Imuni, we're building an atlas of the immune system in order to use the insights from that to help improve treatments for a wide variety of diseases, including cancer. Our pipeline at Imuni starts with actual blood samples taken from patients who have undergone different treatments. Those blood samples are then processed in our lab using many different and complex steps, and then are sent for DNA sequencing. The results of that sequencing are gene expression matrices, tens of thousands of rows and hundreds of thousands of lines, the gene expression profile of each individual cell in the blood. Those matrices are then sent to our computational pipeline, which is what I'm going to talk about today. And then the results of that are sent to both machine learning algorithms and immunologists to extract meaningful insights. Our pipeline contains Google Cloud Functions, which is the same as Lambda in the Amazon infrastructure, and several VMs. So, here's the outline of this presentation. I'm going to talk briefly about what microservices are, and then present the cons and pros of unit tests and system tests, and then present our own approach of stateful mocks, which combine the pros of both unit tests and system tests. And finally, I'm going to talk about the implementation for Google Cloud Functions using Python, which makes all this easy and possible. So what I'm hoping you'll learn is how to combine the pros of both unit tests and system tests. Application for Google Cloud Functions, again, the Lambda in Amazon, and how Python makes this possible. So microservices, they're great, they're scalable, they separate responsibilities, they enable faster development, and are easier to test. You know the rest. Except maybe they're not easier to test. The problem is that while each microservice has, hopefully, its own responsibility, the relationships between microservices are complex. Here I try to show the relationships between microservices that are needed to make coffee in the office, and I'm sure I missed a lot of things, but still this is incredibly complex. So, why are microservices so difficult to test? So, one thing is error conditions. Those are really hard to replicate. Hardware errors and lots of objects are hard to replicate or take a lot of time to set up. Failures in other services, both from bugs and network outages, are difficult to replicate. Subtle timing issues are usually impossible to replicate consistently. Relationships between services are complex, and there are a lot more reasons. So the first solution are unit tests. For each unit test, you set up the condition, the exact state of the system as you want it, then call a specific function, and finally you verify the results of running that function, sometimes even going as far as testing the exact function that function called with the exact parameters, rather than the slightly better solution, which is testing the results of calling that function. So unit tests are fast to write and are fast to run, which also helps the speed of writing them. And it's easy to simulate errors because you set up the entire state of the system before running that function, and you can simulate anything you want. But unit tests require a lot of boilerplate code because typically you set up similar conditions, different but similar conditions for a lot of different tests. That makes them repetitive and long because you have a lot of code setting up the state, then one line calling the function you're testing, and finally a lot of line testing that the condition you expected after running the function is the condition you expected. They're also boring to write and even worse to read. That means that coverage is questionable. You never know what exactly is tested, what's not tested, what conditions you checked and what conditions you didn't check, and you never know if you have a complete test of the system once the function is run. So it's impossible to know what was tested and what was not, and it's even worse when you change functionality or add functionality. If you change functionality, you might end up changing a lot of tests, maybe even all of them. So people turn to system tests. System tests are great. The real-world testing, you set up a different environment from your production environment and just run tests on that. But those tests are slow to run and hence are slow to write because every small bug takes a lot of time to manifest in the test itself. It's hard to simulate errors. You don't want to add hooks for error injections in your code, but sometimes that's inevitable. Timing issues are nearly impossible to replicate and probably impossible to do that consistently. And they're expensive in resources because you need a copy of your production environment or at least a smaller copy of it. So we are using a different approach, using stateful mocks. So each of our microservices is wrapped in its own mock of the environment and thinks it runs in a real cloud environment, except it's running in a simple Python process on whoever is running the tests. All the other services that we use in the cloud, for example, databases or storage, are mocked using stateful mocks that behave exactly like the real thing. And the microservices that we're testing think they run in the cloud, and we never change their code. Okay, so those stateful mocks, they behave like the real thing. They have the same APIs, and whenever an API is called, the result is reflected in subsequent calls to that API. For example, if the mock of the storage is called to copy a blob from one bucket to another, then the next time that bucket is examined, the blob will be there. Now, I have to say, we only mock the exact APIs that we use. We don't need the entire API repository of that real service. That makes them easy to write because they're short. Tens of lines of code, maybe low hundreds for especially complex microservices. You don't need redundancy or resilience or fault tolerance because if there's a bug in the mock, only the test failed and you can easily fix that. If you run out of resources, then it's easy to run the test on a bigger machine. And they only need minimal resources and minimal efficiency because they typically require little resources and the tests run fast enough as it is. And it's easy to add hooks for error injection. You don't have the risk of accidentally triggering those error hooks in your production environment because those hooks are only in the mocked environment. That makes those tests safe. The microservices that we're writing, that we're interested in testing, are wrapped in a runner. That's a Python code that mimics the cloud environment for our microservices. Each microservice is running its own separate Python process. That makes them separate from the test environment, which enables the test environment to import any code it wants without contaminating the microservices. Inside the runner, the local service thinks it imports the APIs of the real services, but instead the runner makes sure it imports instead the same API but of the mocked service, so that is controlled by us. Specifically, it also imports a mock of requests. Now, requests is a Python package that sends HTTP requests to other services. Instead, since you are running all the services on a specific machine, even a developer's laptop, request actually runs the other microservice as a separate process, calls the specific function with the parameters that were supposedly sent via request, and then interprets the results and returns those results to the calling microservice. Specifically, the results of the call are printed by the runner of the called microservice to standard output, and that is saved to the disk, and the calling microservice reads those files and returns them to the calling function, to the calling microservice. The other services that are used by that microservice are also mocks. The implementation of stateful mocks is simple. We replace all the complex machinery that we have in the real services with simple Python data structures. So database tables are just lists in memory, lists of dictionaries. NoSQL databases are just dictionaries in memory. Storage blobs are replaced by local files and on the local machine, but most of the time we don't need the content of those blobs, so we can skip them entirely and just pretend they're there, and the storage metadata, which we do need, is replaced again by a dictionary in memory. Slack messages that our microservices send to different Slack channels to communicate with people are stored again as a list in memory, and all those data structures can be inspected both by people once the test is run or by the test machinery itself. So the test can, for example, make sure that the right Slack messages were sent and the right objects are stored in the database or in storage. What do you mock when you're using stateful mock? So, of course, external services, all external services that your subprocess uses. For example, storage, communication, as I said, we replace the request module by our own implementation. Databases are mocked, and sometimes you also might want to mock your own microservices. If the test is concentrated on a specific microservice, you might want to mock the other microservices and make sure that you control the environment entirely, including, for example, simulating error conditions that are difficult to simulate using the real microservice. Debugging those tests and debugging the code is very easy using this infrastructure because everything is local on the developer's machine. So all logs are just kept in a specific directory on the machine. All messages between microservices are logged and saved in simple files. The status for storage is again just a file or several files on the machine, the same as the content of databases, which is just JSON file. If you want statistics, those are available too. How many times, for example, each microservice was called by which microservice, how long it took to run each microservices, and on and on. Now, it's important to say that mocks have two interfaces. One is a simulation of the real interface of the simulated microservice. For example, copying blobs from one bucket to another, or adding a record for a database. The other interface is meant for the test itself. For example, it makes it easy to examine the condition, the status of storage, or test if there were errors in the log messages. And it's also used to set up the condition before the test runs. For example, defining which buckets are available for the test and which blobs are in those buckets before the test runs. Error injection in order to test the resiliency of your microservices is also easy. All messages can be easily intercepted because those are sent using our own mocks. It's easy to create error messages under different conditions because you can pause any microservice whenever it tries to communicate with outside environment and change the conditions underneath its feet. And mocks can return error messages however many times we want. So, for example, if you want to test the resiliency of our microservice and make sure that it can handle several outages from storage, we can tell the storage to return an error 5 times and make sure that our own microservice tries again and again. But if it fails the 6th time, then the microservice just gives up in order to prevent an infinite loop. Timing issues are also mostly easy to test using this infrastructure. So the time module can also be mocked. So that I'll explain in a minute. And you can test timeouts, for example, very quickly by just skipping 5 minutes in the time module. So whenever a microservice checks the time, it will a microsecond later it will think the time that 5 minutes have passed. And of course, services can be paused at every interface, and the timing can change. Now, the time module cannot be mocked because it's a basic part of the Python language. What you can do instead is monkey patch it. That means replacing the functions that are called by your microservices by your own functions, instead of replacing the whole module. Okay, just a recap of what I talked about so far. So with Stateful Mocks, you get full access to all state, both by the test code to test that everything that should have happened did in fact happen, and by the user if the test fails or code has changed, or while writing the tests. Those tests are fast, much faster than system tests, although they're somewhat slower than unit tests. But that's understandable, they test a lot more. You don't need any network access. Everything is local because everything that is accessed through the network is either run as a process on your own machine or is mocked. That means that you don't need credentials, and it's much safer, and it's easy to run those sets using an ECI/CD environment, even if it's not yours. It doesn't interfere with any production environment because you don't change any of your actual code. The only error injection code are in the mocks. You don't need repetitive code since those mocks are stateful. They know how to behave once their APIs are called. You don't need to repeat the same setup code. You don't need to set up the exact same conditions. You just use those APIs. And it's easy to write a simulation of complete system tests using this system. In fact, it's easier to write more complex tests because those tests are much faster and easier to write, and you can easily get the status of the entire system. So let's talk a bit about mocking Python packages. The first and most important thing is to control your sys.path. That's the path of where Python packages are taken from when they are imported. So if the first thing in sys.path is the path of your mocks, then whenever your microservices think they import the API of the real service, they actually import the mock. You only need to mock the things the APIs that you need. You don't need to even write any other APIs, except those APIs that are imported but are not used. So the best thing here is to write the same API, but just raise a not implemented error. And once you write a test that actually uses that API, the test will fail, and you can just go back, examine the logs, see that the mock did not implement that API, and just add it. And hopefully the next time you run the test, it will succeed. The time module cannot be mocked easily, but you can replace those specific functions that you use with your own function using just monkey patching. And we use the disk as a shared status, so whenever the mock examines this, for example, the mock of the storage examines the storage status, it saves this status on disk, and when the next time it runs, whatever changes it made are reflected back. So we use Google Cloud Functions. As I said, this is the equivalent of Lambda in the Amazon Cloud. When those Google Cloud Functions call one another, we actually run the other Google Cloud Function as a different Python process wrapped in a wrapper that simulates the cloud environment. Each of those Google Cloud Functions is run in its own separate process to isolate it from the test environment. And that means that the test can import whatever code it wants without influencing the microservices that we test, the Google Cloud Functions that we test. The mock of the request module takes care of that, and we don't need to change anything about the code of the real cloud function. The mock of request also records the transactions, so we can examine them later and see if we have any inefficiency in calling those Google Cloud Functions. So I talked a lot about how to implement this in Python, but just to reiterate, we run each Google Cloud Function in its own Python process that runs a runner, which in itself runs a Google Cloud Function and makes sure that whenever that Google Cloud Function imports an API, it's actually the mock of the API. Just to finish, this approach also has its own challenges. The first thing, which is actually common to all tests, is that services might change. In that case, hopefully the test will fail, and then you can fix them or write new tests. When external services are changed, the test will not fail, but this means that you also need some system tests to make sure that you track changes in an external environment. That said, cloud APIs tend to remain fixed because they influence a lot of customers, and Google and Amazon and other cloud service providers cannot do that to all of their customers. The timing in those tests might be different, so you might miss some race conditions, but again, that's a disadvantage of all testing. Again, those tests are also not exactly real world, but again, you do what you can. And one final note, those tests could be faster. It turns out that just running the Python process, the Python program takes 150 milliseconds. Doesn't sound like a lot, but we run about 1,000 of them in our test. That's 2.5 minutes. That's acceptable, but it's a long time. If we had 10 times the number of services, what we could do is run each of those microservices as its own process and call them using RPC, so we save the loading time. This will be about a day of work to change the entire infrastructure of the test to use that, but so far we haven't found the need for that. Thank you.